To show you a very efficient method to um, differentiate you with first principle. So differentiating with first principle involves basically taking a small change in x, which results in a small change in y, and then you have to go stepwise and then take limit at the end to get your gradient. So, but that is very difficult going the conventional way. So, for example, showing the conventional way to differentiate with first principle, or what you would call differentiation by definition. So, let's say this question, for example. So, for this question, it's y equals to x cubed plus x squared. To differentiate by definition or by first principle. So, you take a small change in y, at delta y, and that also results in a small change in x, delta x, and delta x. So you substitute it into the equation of y equals to x cubed plus x squared. After substituting into that equation, you end up with y plus delta y, and then you expand these brackets. Now that is the reason why the conventional method is very difficult using first principle of definition, because these expansions they take a lot of time. Of course you can use binomial expansion, but if you have a value of, like in the initial question I showed, say the bracket is raised to 30, then it becomes very difficult for you to expand it even with the help of binomial theorem. But regardless, let's just go through the first principle. So you expand the two brackets and then you collect the like terms. So the ones without delta x, you collect them. And what you see is that when you substitute your initial y equals to x cubed plus x squared here, they will cancel out with those that don't have delta x. And so with that, you are left with delta x is equals to 3x squared plus delta x plus 3x plus delta x squared plus delta x cubed plus 2x delta x, and then delta x squared. Of course, you can go on further and collect like terms and the rest of it. But the next step is to divide by delta x. So when you divide by delta x, you'll see that delta x will cancel here, and then delta x and delta x, or 1 delta x, will be cancelled out, and same goes through. And so you are left with this one, 3x squared plus 3x delta x squared plus 2x and delta x. Next, you take the limit as delta x implies 0. Delta y upon delta x will imply the gradient, which is dy upon dx. And so therefore dy upon dx equals 3x squared plus 3x. Remember that delta x implies 0. And so you substitute 0 wherever you see delta x. So it becomes this, and then you have your final gradient, which is 3x squared plus 2x. Now you can verify with the formula and you will see that this is the correct um, um, differentiation with the formula. But this is the method by the first principle. Now there is a better method to solve it, and that's the new trick I want to show. So the better method to solve using first principle is by using the binomial approximation. So let's say it's the same question. Same step, we take a small change in x, results in a small change in y, and then we substitute it in the initial equation. And then here, what we are going to do, we are not going to expand, we are going to take a shortcut. So what we are going to do, we are going to factor out x. Now the reason why we factor x out of each of these brackets is because when you do that, you will see that delta x will be divided by x. Now remember, delta x is a small change. If you have done calculus, the introduction, delta x is a very small change. And so if you divide delta x by x, it becomes even smaller. So you don't factor out delta x, because if you factor out delta x, you won't get this value as being very small. So you factor out x. So when you factor out x, you get a small value, which is delta x, being divided by another value to even form an even more smaller value at this point. Now, once you have done this factorization, of course, if you factor out x of this, it becomes x cubed and then the bracket gets the cube as well. Same here, if you factor out x, so x now becomes x square, and then 1 plus delta x takes the square as well. Now, the binomial approximation law states that if you have 1 plus a raised to the power n, but if a is a very small value, then approximately you can expand this as 1 plus the power times this variable. So that's 1 plus ne, provided if a is small. So that is why you have to divide by x, because if you divide by delta x, it becomes x divided by delta x. If you factor out delta x, it becomes x divided by delta x. And x divided by delta x is not small. And so this won't work. This law won't hold. But if you take delta x and divide it by x, remember delta x is a very small change. And so this law holds if you do it this way. And so your next step is, since this is 2, then using this law to expand this bracket, it becomes 1 plus the power 3 times this term. So it becomes 1 plus 3 delta x upon x. So you multiply the power by this term. Same for this. If you use this method to expand this, it becomes 1 plus 2 times this term. Okay. And then your next step will be to expand this bracket further. So you have y plus delta y, and then you expand it, it becomes x cubed times 1 x cubed, and then x cubed times this. You have x below, so x will cancel 1 x out here, so it becomes 3x square and delta x. Okay, same here, you multiply x times 1 x square, and then x times this term, x will cancel 1 x here, and it remains 2x delta x. Now, with that, you can substitute here what y stands for. So y is x cubed plus x squared. When you substitute here, you will see that it will cancel out with x cubed and x squared here if you collect these two terms without delta x. And so what you are left with is delta y is equals to this. So this term, 3x squared plus delta x plus 2x plus delta x. And you can divide by delta x. And what you are left with is delta x upon delta y is equal to 3x squared plus 2x. And if you take limit as delta x implies 0, delta y upon delta x equals dy upon dx, you are left with the same thing we got initially, which you can confirm by the formula method. Now, of course, it doesn't seem as much of a difference compared to the initial standard differentiation by first principle, but it really makes a big change. For example, let's say you have a question like this one. So I want you to try solving it using the conventional method. What you will notice is that it's very difficult to solve this via the conventional method, because how would you do it? If it were only just x to the fourth root, then maybe you can think about um, taken to the power 4 on both sides to get rid of this fourth root. So it becomes impossible to solve, and hence that formula comes into play. So this is how using the approximation method is very useful to solve using first principle. So if you're ever faced with this type of question, what you're going to do is you are going to take the same steps. So you will see that it's very easy, very straightforward, no difference. So this method works for every problem. So same thing, this is the question. You can write it in the index form. And then y plus delta y, you take a small change in x, it results in a small change in y. Then you have this. And then next you substitute y is equals to this, so you can substitute it here. And then, of course, you factorize x out. If you factorize x out, it becomes x to the power 4. And then remember, this is now 1 because you have factorized x out. So it becomes 1 plus delta x upon x raised to 1 upon 4. Same here. Same thing. Factorize x, it becomes 1 plus delta x. And then your x to the power half is outside. Now, of course, you know the rule, 1 plus a to the n. If a is very small, such as when delta x is such a small change, then you can expand this bracket by just multiplying the power by this term. So therefore, we carry on forward. So we can raise this to the index form. this value we have just substituted, and then we basically rewrite this using this formula. So we take the power and multiply it by this term. So you have delta x plus 4x plus, same for this. You take the power and multiply it by this term. So you have delta x plus 2x. Okay, good. Now your next step is to expand the bracket. So if you expand the bracket, you get x to the 1/4. And then, of course, you know that this multiplied by this term, x is here and x is here, so it becomes x to the 1/4 divided by 4x. And if you do it that way, they have the same basis, so you have to subtract the parts since they are dividing. And so if you subtract 1/4 minus 1 here, you have minus 3/4 here. Same for this one. You multiply this by this, you get this. And then here you have x to the half divided by 2x. So 2x half minus 1 gives you minus half here. And then the 2 stays underneath. So you get that. Now the next step, of course, you can see that this one will cancel this one. And then this one will cancel this one. And so you are left with delta y is equals to this term and this term, since these two are cancelled. And so once you have these two terms, you can go on further and divide by delta x. So if you divide by delta x throughout, you'll see that delta x will be cancelled and delta x will be cancelled here. And so you're left with delta y upon delta x is equals to x to the minus 3 upon 4 plus x to the minus half upon 2. And if you take your limits, delta y upon delta x implies the y upon dx. You are left with dy upon dx is equals to this term, because delta y upon dx now becomes dy upon dx. And you can rewrite this in your root form. And so it's very simple. So an impossible question you can solve in just one page, which will have required you so much steps. Okay, so let's start with the question in the beginning. Let's go over it. So suppose you are faced with this impossible expansion question by the conventional method, y to the x to the 100. How do you expand this? Even using your binomial theorem, it will be very difficult to expand this. So if someone were to ask you to differentiate using the first principle, it is almost impossible unless you use the formula. But you can do it using this new method I've just shown you. So if you take the same steps, take your small change in x, which results in a small change in y, and then you take x to the 100. You substitute now, you know that y is x to the 100, so you substitute it here. And then for here, you factorize your x out, so it becomes x to the 100, 1 plus delta x divided by x. And then you write your law, which states that 1 plus a to the n is equal to this if a is very, very small. And so with that, we are left with here. So to expand this one now, it becomes 1 plus this term multiplied by the power, so times 100. And so with that, we expand the bracket, so it becomes x to the 100 plus 100 x to the 90 to the 99, because you know there is x here which will cancel out 1x here, so it becomes x to the 99 delta x. So with that, you divide, I mean, this one will cancel this one, and so you're left with delta y, which will be equals to this term. And so you divide by delta x on both sides, delta x will be cancelled out, and you take your limit next, as delta x implies 0. Delta y upon delta x implies dy upon dx, and your dy upon dx equals to 100 plus x. And so such a long problem, if you would have solved it using the conventional method, has now been condensed into just few lines. And so this is the method. So I'll advise you to try it for various problems. It's just a simple method wherein after substituting your delta x, instead of going through expansions or whatever, all you need to do is that as long as there is a power, or even if there is no power, or the power is 1 or half or something, you can always know that 1 plus a to the n, when you expand it, since delta x, you are holding to the law that delta x is a very small change, then it should be 1 plus na. And once you have that, you can solve any problem, any difficult problem, whether it's the square root, it's a fourth root, it's 3/4. So it becomes very easy. It doesn't matter the problem. You can solve it using differentiation. So anything, let me know in the comments. Please like, subscribe, and thank you all for watching.